Okay, some students asked for some video help for the homework, which is due on Thursday, and so I put this together. This is similar material which we will do tomorrow in class, but just if you wanted to have some more time to do your homework, here it is. Okay, so we've been doing extensive form games, that is, games in which people move in sequence, and there are three main ideas. Okay? One is, what is a strategy? So to specify a person's strategy, you have to write down an arrow from all of her nodes. That is, a person might have several nodes, and you have to write down an arrow in each one of them, all of them, okay, including those which are not necessarily reached. Okay. In other words, a strategy is a complete contingent plan. It's a plan which will specify what you do in all contingencies. So I'll illustrate this in an example coming up. Okay, the second point is subgame perfection. Okay, so when you take an extensive form game and put it into a table, a strategic form game in other words, you can find Nash equilibria, but then we said, well, some of them are sketchy, some of them are kind of strange, and the good ones we called subgame perfect. So Nash equilibrium is subgame perfect if in every subgame people's actions correspond to a Nash equilibria in that subgame. In other words, in a subgame perfect Nash equilibrium, there are no non-credible threats. Okay, so in an extensive form game, there might be several Nash equilibria. Some will be subgame perfect, some will be not. Okay. And finally, the third point, which we haven't gotten to yet, so this is new, this bit is new, it's called backward induction. So backward induction is a method of finding subgame perfect Nash equilibria, which is faster. In other words, you don't have to do this whole table thing. You can simply look at the game itself, the tree, and use this method of backward induction and find subgame perfect Nash equilibria. So this is something which, again, I'll introduce in this example. Okay, here we have an example. It's high school prom. Okay, first, person 1 can either ask or not. Okay, if person 1 asks, then 2 can either refuse or go. Okay, and finally, if 2 refuses, then 1 can either choose to serenade or not. Okay, so first 1 either asks or not. Okay, if 1 doesn't ask, then of course the game's over. If 1 asks, then 2 goes, then the game's over too. If 2 refuses, then 1 can sort of heighten the stakes by saying, oh, I'll serenade you or not. Okay, so what are the payoffs? If nothing happens, it's 0-0. If 1 asks and 2 goes, 1 really likes that, but 2 doesn't like it very much. Okay. If 1 asks, 2 refuses, and then 1 doesn't do anything, in other words, sort of 1 backs down, then 1 is also unhappy. 2 is also unhappy, but not as happy as if 2 had to go. Okay. And finally, if 1 serenades, it's just like bad for everybody. Okay, it's just an embarrassing situation. Okay, this is our game. So the interesting question is like, will 1's threat of serenading or not kind of compel 2 to go or not? That's kind of an interesting question. Okay, all right. So here's our game again. So what we did last time so far is we turned this game into a strategic form game. How do I do that? Well, remember what a strategy is. A strategy is a complete contingent plan. 2 strategy is easy because 2 just has 1 node, so 2 either refuses or goes, right? But what's 1 strategy? 1 can either ask or not at this node, and also 1 can either serenade or not at this node. So actually 1 has 4 strategies, right? A choice of what to do here, 1 or 2 choices here, and a choice of what to do here. Okay, so it looks like this. Again, 2's strategies are simple: either refuse or go. 1 can either ask and then serenade, ask and then not serenade, not ask, serenade, and not ask, not serenade. Okay, so 1 has 4 strategies. Okay. Now, there's a question which often comes up, which is, if 1 doesn't ask, why should we worry about, well, 1's, oh shucks, let me fix this. Okay. This should be serenade. Okay. Okay, so if 1 asks, so of course then there's an issue of serenade or not serenade. But if 1 doesn't ask, why should we worry about whether 1 serenades or not, right? Because if you never ask, then the whole issue of serenading doesn't even come up. Okay. In other words, why do we have these two strategies? Shouldn't we just have like one strategy, not ask? Okay, and that's not an unreasonable point. But remember, the definition is that a strategy must specify what you do in all nodes. Okay, it must specify what you do in so-called. A strategy is a complete contingent plan. You have to write down an arrow from all of our nodes. Okay, so in other words, it's not enough to simply say not. Okay, you have to say not and serenade, or not and not. You have to specify what happens in all of one's nodes, even those nodes which do not occur. Okay, so that's the definition. All right, it's not this. Right? Another way to say this, again, so to specify a person's strategy, you have to write down an arrow from all of our nodes, even those not reached. Okay, so this is the graphical way of doing it. Again, so this is ask and then serenade. This is ask and not serenade. This is not ask and then serenade. This is not ask and then not serenade. Okay, so then we filled in these numbers. I did them already. Notice again, if 1 doesn't ask, then it doesn't matter what 2 does. It's just a plain old 0, 0, right? And that's true if 1 plays this strategy of not ask, serenade, or not ask, not serenade, right? If 1 doesn't ask, it's just zeros, okay? How about these other ones? If 1 asks, 2 refuses, and then 1 serenades, that's the thing which is worse for everybody, okay? If 1 asks, 2 goes, that's the best for 1, but 2 doesn't like it very much. If 1 asks and 2 refuses, and then 1 doesn't serenade, okay, that's kind of 2. That's pretty good for 2, although 2 would rather have not have been asked in the first place. 1 doesn't like that. 1, doesn't want to be refused. Okay, and then finally, if 1 asks, 2 goes, and then again, what's the best thing for 1? Okay, so this is our strategic form game. Let's see if we can find Nash equilibria. Let's see. Can we do this? Okay, if 2 plays this, then the best response is this. If 2 plays this, the best response is up here. These are hundreds. If 1 plays this, the best response for 2 is this -10. Okay, this is -5 is the best response, and then there's just a bunch of zeros. Okay, so what are our Nash equilibria? We have 3. This one, and this one. So we have this, this, and this. And I think I wrote them down here. So the first one is what? Ask, serenade, and then 2 goes. Okay, and this is kind of like where the threat worked, right? 2 is going because 1 is threatening to serenade. And this one is where 1 doesn't ask, 2 refuses, and then 1 serenades. Okay. This is where 1 doesn't ask, 2 refuses, and 1 doesn't serenade. Okay, so let's see. Wrote those down. Oh yeah. Okay, so these are the 3 Nash equilibria. 1 is doesn't ask, serenade, refuse. That corresponds to what? Ask, serenade. That's this one. Okay. Not ask and not serenade. Refuse. That's this one here. Okay. And finally we have this one. Ask, serenade, go. I think that's ask, serenade, go is this guy. Okay. Alright, these are 3 Nash equilibria. Okay. Which are subgame perfect. Okay, so what we do is let's take this one, not ask, serenade, refuse. So the way you check whether it's subgame perfect using the definition is you write down the arrows. So person 1's strategy is 1 is not asking, and then 1 serenades. We write down those arrows. 2 refuses. Okay, so then we go, now that we've written down the arrows in this game, we look at each subgame. Okay, is this Nash equilibrium subgame perfect? Okay, well, that's 1 subgame. Okay, if I were to show you this game alone, would this be a Nash equilibrium? In other words, is 1 doing a best response? Okay, well, I think the answer is no, because 1 is choosing -100 over -50. I'm never to show you this game alone. It's not a Nash equilibrium. In other words, 1 threatening to serenade is not credible, right? 1 doesn't want to actually serenade. If we came to that point, 1 would rather choose the minus 50 over minus 100. So this does not correspond to Nash equilibrium. Okay, so therefore, because it's not a Nash equilibrium, the subgame, this overall Nash equilibrium is not subgame perfect. Make sense? Okay, so therefore, this first Nash equilibrium is not subgame perfect. How about the second one? Okay, this is not ask, not serenade, refuse. Okay, so here 1 is playing not ask. 1 doesn't serenade, so we put that little arrow there. And then 2 refuses. Okay, so let's check. We have to check every subgame. Okay, is this Nash equilibrium subgame perfect? Okay, first we check that subgame. Is person 1's action here, does it correspond to a Nash equilibrium of the subgame? And the answer is yes. Minus 50 is bigger than minus 100, so 1 is doing the best response. It does correspond to a Nash equilibrium of the subgame. Now we have to check the next subgame. Bloop. Okay, now 2 is playing refuse. We have to check whether 2 can gain by deviating. So 2 in the end is getting what? Minus 5. If 2 were to deviate, 2 would get minus 10. So 2 cannot gain by deviating, and therefore this is a Nash equilibrium. 2 is best responding. Also in this subgame, people's actions correspond to a Nash equilibrium of the subgame. Okay. All right, then finally, if we do the whole game itself, then we can check similarly that 1's playing 0 is the best response, right? 1 is getting 0 by playing not. If 1 were to ask, 2 would refuse, and then 1 would play down here, so we get minus 50. So by 1 playing not, this 0 is better than minus 50, so 1's playing a best response. So since we checked every single subgame, first this subgame here, and then this subgame, and then the whole thing, okay? In all of the subgames, people's actions correspond to a Nash equilibrium in that subgame. Okay, because that's true for all these subgames. This is subgame perfect. This Nash equilibrium is subgame perfect, and we have a subgame perfect Nash equilibrium. Okay? All right. So the first one wasn't subgame perfect. The second one is. Let's just do the third one. Okay. This is the one where kind of the threat works. Okay. This is where 1 asks and then serenades. Let me fix that to make it the same as everything else. And then I'll make the colors too. Okay, so this last one, this is when 1 asks and then serenade, and then 2 goes. So 1 now, there's an ask there. 2 goes. Oh, sorry, 1 asks and then serenades, right? 1 asks, and then serenades, then 2 goes. Okay, is this subgame perfect? So again, the definitions, we have to look at each subgame. Okay, take a look at that little subgame there. Is 1 playing a best response in the subgame? Well, 1's getting a minus 100 as opposed to minus 50, so the answer is no. 1 is not playing a Nash equilibrium in the subgame, right? So, 1's action, the subgame does not correspond to Nash equilibrium. Okay, therefore this whole situation is not subgame perfect. There's 1's threat to serenade is not credible. Okay? Alright, so what do? We found 3 Nash equilibria, and this last one's not subgame perfect. So this one was not subgame perfect, this one is not, but this one was. Okay? Any questions? Okay, so is there an easy way to do this? And this is our third little point. There were 3 points. One was understanding what a strategy was. A strategy is a complete contingent plan. You have to write down an arrow from every single node. That's the first point. The second point was the definition of subgame perfect Nash equilibrium. And Nash equilibrium subgame perfect if in every subgame people's actions correspond to a Nash equilibrium of that subgame. And this is the third point, which is new. Is there an easy way to do this? Okay, well, if you want to find all Nash equilibria of an extensive form game, you must write it as a strategic form game, i.e. a table, and then find the Nash equilibria. So if you're in a situation where, like the high school prom example, to find all Nash equilibria, you have to write it down as a table. Okay. However, if you want to find only the subgame perfect Nash equilibria, Okay, in other words, you think that people cannot play non-credible threats. In other words, people are just going to play credible threats. If you want to find only the subgame perfect Nash equilibria, then the easy way to find them, the fast way to do it, is to use so-called backward induction. Okay, this is the third point we're going to talk about. Okay. All right. What is backward induction? To use backward induction, you start with the end of the game, figure out each person's best response at each node, and then work your way backwards. So again, induction, what does induction mean? It means sort of iteration, like start first and then keep on going backward. And it's backward because you start at the end of the game and work your way to forward. Okay. So let me show you how that works. Here is my high school prime example, and remember when we found all Nash equilibria, there were 3. Okay. One of them was subgame perfect. We found the 3 Nash equilibria by making it to a table, and in particular we found one where one's threat of serenading worked. Okay, it sort of forced person 2 to go. Okay. That was not subgame perfect, right? Because one threatening to serenade was not credible. Okay, if I want to find just, so remember I found 3 Nash equilibria, only one was subgame perfect. If I only wanted to find just that one, only the subgame perfect Nash equilibria, then I don't have to do the whole table thing. Okay, what I can do is this method of backward induction. How does that work? You start with the end, okay, i.e. here, one's decision. One either chooses to serenade or not. Okay, so if one gets to make a decision at this point, what does one do? Well, one chooses this minus 50, right? Minus 50 is bigger than minus 100. Okay, so one's choice at this point would be to not serenade. Okay, one chooses not because minus 50 is bigger than minus 100. Okay, now we work our way backwards. We have established that one doesn't serenade, right? So now we look at person 2's decision here. 2 can either refuse or go. If 2 goes, 2 gets minus 10. If 2 refuses, 1 will then for not serenade. That's what we just figured out. If 2 refuses, 2 will eventually get minus 5. Okay, so 2 is choosing between this minus 10 if 2 goes, or this minus 5 if 2 refuses. Okay, so which is bigger? Well, the minus 5 is bigger than minus 10, so therefore 2 will refuse. Okay, that's 2's best response. 2 chooses refuse because minus 5 is bigger than minus 10. Okay, now again we work our way backward. Now we have person 1's decision here. 1 can either not go and get a 0, sorry, not ask and get a 0, or ask, and if 1 asks, then 2 will refuse, and then 1 will not serenade. So if 1 asks, 1 in the end gets minus 50. Okay, so 1's choosing between 0 and minus 50, and the bigger one is 0, so therefore 1 will not ask. Okay, so the way to think of it is this, right? 1's threat of serenade is not going to work, right? It's not credible. Given that, 2 is not going to go. 2 is going to say, well, yeah, I know you're not going to serenade me. You're just that's just all talk because you would be so embarrassed. That's just being so embarrassing. You would never do that. Therefore, I'll refuse. And then given that, 1 says, oh, I'd rather not have asked in the first place. I just won't ask. Okay? All right. 1 chooses not because 0 is bigger than this minus 50. Okay. So, again, let me fix it. This is our subgame perfect Nash equilibrium, and I'll just, not ask. Not serenade. Put the colors in there too. Okay. Okay, so this is, we found this using backward induction, okay? It's the one where 1 doesn't ask, doesn't serenade, 2 refuses. Okay, this is the subgame perfect Nash equilibrium. We found it using backward induction. So remember, to find all Nash equilibria, you have to do the table, and we found 3. Okay, one of them was subgame perfect. This is another way of finding just the subgame perfect one, and we did it without looking at the table. We didn't have to write down the table. Okay, we found it using so-called backward induction. That's the method. You start at the end. You try to figure out each person's best response, and once you've written down that, then you kind of go backward and backward. Okay, that's backward induction, how it works. Let's just do another backward induction example. Kidnapping, remember the very first example we did? Okay, so how do I use backward induction? I start with the end. The family can either pay or not. Okay, which is the bigger number? Family's choosing between minus 20 and minus 100. Minus 20 is bigger, so the family pays. Given that, the kidnapper can either not kidnap and get a 0, or kidnap and get a 10. Okay, which is bigger? Well, the 10. Okay, so this is the subgame perfect Nash equilibrium. Okay. Remember, in this case, there were two Nash equilibria. One, this one, right? And the other one is where the kidnapper doesn't kidnap because the family doesn't pay. Okay, that was not subgame perfect. Okay, this is subgame perfect, however. Okay, so if there are no ties, there's only one subgame perfect Nash equilibrium. So if there are never any ties, there's only one subgame perfect Nash equilibrium. Why? It's because anytime somebody makes a choice, it's determined. You just choose the biggest number. There's always one biggest number because there are no ties. However, if there is a tie, then more than one SPNE is possible. For example, this is our penalty kick with ESP example. How do we use backward induction? Okay. Say the striker goes either east or west here, which is bigger, 1, 0. Striker shooting to 1, 0. Of course, this one is bigger. The striker will go west in this node. In this node, the striker will go east because 1 is bigger than 0. Given that, the goalie can go either east and get a 0, or the goalie can go west and get a 0. That's a tie. Both are equally bad. Okay, so this is one subgame perfect Nash equilibrium, which the goalie chooses east. Okay, and another, so this is one subgame perfect Nash equilibrium. Another subgame perfect Nash equilibrium is when the goalie chooses west. Okay, and what is the subgame perfect Nash equilibrium? It's the pattern of arrows I'm drawing. Remember, a strategy has to specify what happens in each node. Okay, so this is this entire pattern of arrows is the subgame perfect Nash equilibrium. And in this case, there's two. Okay, there's this one and the one we had before, which is that one. Okay. All right. How about this example? Okay, here, 1 chooses between A and B, then 2 chooses between A and B. Okay, in this case, let's see, 2 has a tie between these 5s, and say that 2 chooses that A, right, just arbitrarily. If 2 chooses A, then 1 is choosing between this 10 and the 9, so 1 will choose A because 10 is bigger than 9. This is a subgame perfect Nash equilibrium. It's the same game. Now say here 2 chooses, instead of A, 2 chooses B. Okay, that is this 5. Okay. Now given that 1 is choosing between 8 and 9, and now 1 chooses 9. Okay, this is also subgame perfect Nash equilibrium. So this game is a little different than the penalty kick with ESP example. In the penalty kick with ESP example, kind of how the tie didn't really make any difference, right? Again, the goalie could either go east or west. It doesn't make any difference. The goalie loses either way. Here 2 has a tie, but how 2 breaks the tie affects 1, right? If 2 breaks the tie in favor of A, then 1 will want to play A. If 2 breaks the tie in favor of B, then 1 will play B. In any case, both of these satisfy the definition of subgame perfect Nash equilibrium. So it's possible for there to be more than one SPNE if there's ties. Okay. All right, I'll just quit there. Maybe I'll do another video based on the homework.